Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein at a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving. This is the old-fashioned principle of relativity. But the point is that the switcheroo changes relative things like position and velocity, and not absolute ones like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same, well, time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick. And it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
Galilean relativity. One of its major principles is that Newton's laws of motions are valid in all inertial reference frames. Reference frame is a coordinate system in which experimenters equipped with meter sticks, stopwatches, and any other needed equipment make position and time measurements on moving objects. Time dilation. Time dilation is one of the principles of relativity that has driven us to logical conclusion that the time at which an event occurs may not be the same for two reference frames moving relative to each other. Length contraction. The concept of relativity that is extended to space and distance. Relativistic momentum. The particle velocities in different frames are related by Galilean velocity transformation. Relativistic energy. This concept was Einstein's discovery of fundamental relationship between energy and mass. Einstein's pathway to discovering relativity. It was pondering these developments that led Einstein to discover the special theory of relativity in 1905. The discovery was not momentary. The theory was the outcome of, in Einstein's own reckoning, 7 and more years of work. He even places one of his early landmarks in a thought experiment that he had at the age of 16 in 1896, 9 years before the year of miracles of 1905. Unfortunately, we only have fragmentary sources to document the years of this struggle.
Equations. Time. Proper time, delta r, is the time interval between two events measured in a reference frame, in which the events occur at the same position. The time interval, delta t, between the same two events, in a frame moving with relative velocity v, is where beta equals v over c. This is time dilation. Delta t equals delta torque over the square root of 1 minus b squared is greater than or equal to delta torque. Space. Proper length, cursive L, is the length of an object measured in a reference frame in which the object is at rest. The length, L, in a frame in which the object moves with velocity v is length contraction. Big L equals the square root of 1 minus b squared times length is less than or equal to length. Momentum. The law of conservation of momentum is valid in all inertial reference frames if the momentum of a particle with velocity, cursive u, is p equals y mu, where momentum approaches infinity as u approaches c. Curly y equals 1 over the square root of 1 minus u squared over c squared. Energy. The total energy of a particle is E equals y mc squared. K approaches infinity as u approaches c. The total energy of an isolated system is conserved. E equals mc squared plus y minus 1 times mc squared. mc squared being rest energy, and y minus 1 times mc squared being kinetic energy. Last equation. If an object has a velocity u in frame S and u1 in frame S1, the two velocities are related by the Lorentz velocity transformation. v equals u minus v over 1 minus uv over c squared. U equals u plus v over 1 plus uv over c squared.
Hypothesis. Our hypothesis for this experiment was if person A and person B are moving in the same direction, and person A is moving faster than person B, then the speed recorded from the motion detector on person B will be less than person A's actual speed.
Experiment. Person A is Ben and person B is Tim. At first, Tim was moving at a constant speed with Ben. After 3 trials, Tim moved slower than Ben, but at a constant speed through all 3 of the trials. At last, Tim moved faster than Ben, also with a constant speed, in order to show the theory of relativity. IV, the speed and direction of the person. Levels of the IV, slow, same, and faster than person B. dV, the speed the motion detectors of person B reads on person A, i.e., the speed of person A in perspective of person B. Conclusion. If 2 objects are moving at the same speed, then in the perspective of one of the objects, the other is not moving. If 2 objects are moving in the same direction, but one has a slower speed, then in perspective of the slower object, the faster object is moving slower than it actually is. While in the perspective of the faster object, the slower object appears to be moving faster than it really is. Therefore, all measurements are in perspective of a reference point, and if the reference point is changed, then the measurements might change as well.
The Hayflick-Keating experiment was to test the theory of relativity. In 1971, 2 physicists completed the Hayflick-Keating experiment to test time dilation. Joseph C. Hayflick and Richard E. Keating took 4 season beam atomic clocks aboard commercial airliners. They flew twice around the world, first eastward, then westward, and compared the clocks against others that remained at the United States Naval Observatory. When compared, the sets of clocks were found to disagree with one another, and their differences were consistent with the predictions of special general relativity. The experiment tested 2 different types of time dilation. It first tested kinematics time dilation, and secondly, gravitational time dilation. According to special relativity, the rate of a clock is greatest according to an observer who is at rest with respect to the object. In a frame of reference in which the clock is not at rest, the clock runs more slowly as expressed by the Lorenzo factor. Considering the Haley-Keating experiment in a frame of reference at rest with respect to the center of the Earth, a clock aboard the plane moving eastward in the direction of the Earth's rotation had a greater velocity, resulting in a relative time loss, than the one remaining on the ground, while a clock aboard a plane moving westward against the Earth's rotation had a lower velocity than the one on the ground. The experiment also tests gravitational time dilation. The general relativity predicts an additional effect in which an increase in gravitational potential due to the altitude speeds up the clock. That is, clocks at a higher altitude tick faster than clocks on the Earth's surface. This effect has been confirmed in many tests of general relativity. In the Hayflick-Keating experiment, there was a slight increase in gravitational potential due to the altitude that tended to speed clocks back up. Since the aircraft flew at roughly the same altitude in both directions, this effect was approximately the same for the 2 planes, but nevertheless, it caused a difference in the comparison to the clocks on the ground.
One of the modern uses for relativity is GPS. In order for your car's GPS navigation to function as accurately as it does, satellites have to take relativistic effects into account. This is because even though satellites aren't moving at anything close to speed of light, they're still going pretty fast. The satellites are also sending signals to the ground stations on Earth. These stations and the GPS unit in your car are all experiencing higher acceleration due to gravity than the satellites in orbit do.